Welcome to the Explainer. Today, we're not just looking at a piece of research. Nope, we are cracking a case. The mystery, a super powerful open source AI that was supposed to learn all these complex tasks, but instead it just completely broke down during training. This, my friends, is an AI detective story.
So first, let's get our heads around the dream here. The whole goal was to use this technique called agentic reinforcement learning. Now, this isn't about training an AI to just, answer questions. It's about building a true digital assistant, one that can actually do things for you. We're talking planning a project, writing and testing code, and taking a whole bunch of steps to solve a complex problem all on its own.
A team of engineers at LinkedIn, they set out to train the powerful open source GPT-OSS model for these exact kinds of tasks. But the moment they kick things off, bam, they hit a wall. The model wasn't learning. It was failing. And I mean, it was failing spectacularly. All right, here's our case file. We're going to follow this investigation step by step, right from the initial crime scene all the way to the final verdict. Okay, so the first stage of any investigation, you got to examine the crime scene. And in the world of AI training, the crime scene is all in the data, the logs, and the performance metrics. The team had some pretty clear expectations. As the AI trained, its performance, which in their world they call a reward, it should have been steadily climbing up and up. The training process itself should have been nice and stable. But the reality was the complete opposite. The reward totally flatlined, and the entire training process was just wildly unstable. Nothing was working. And here it is, the first major clue. This chart shows the model's gradients. You can just think of them as learning signals. Now, in a healthy model, that first bar, those signals are low, they're stable. But for GPT-OSS, whoa, they were completely off the charts. This is what's known as exploding gradients. It's like the model is trying to learn so hard and so fast that its internal math just kind of breaks. This was the smoking gun. So let's move on to the first suspect and see how the team chased down an early, but as it turns out, a totally misleading clue. The team's first suspect was a violation of a core rule in their training method, which is called PPO. Think of it this way. PPO demands that the AI learns only from its most recent actions, not from outdated experiences. For all the math to work out, there has to be a perfect one-to-one match, which proves the AI is learning from its current self. And here's what they found. GPT-OS uses something called a mixture of experts architecture. It's like having a whole team of different specialists inside the AI. The problem was, because of these tiny random fluctuations, the AI would sometimes send the exact same problem to a different specialist on a second try. And that broke the perfect one-to-one match. It really looked like the smoking gun. So they applied a patch. It was a diagnostic test to force that ratio back to a perfect 1 and see if it fixed the problem. But it didn't. The gradient still exploded, the reward was still flatlined. This suspect was a dead end. The real culprit was still at large. After hitting that dead end, the team knew they had to dig much, much deeper. And this is where they moved from a simple inconsistency to a really fundamental flaw, leading to the story's big aha moment. Their new hypothesis was something called a training-inference mismatch. In simple terms, this means the rules the AI was following during school, during training, were different from the rules it used on its final exam, during inference. It was basically being taught one thing, but then tested on another. So the investigation led them to this really subtle but critical feature called attention sinks. You can think of these as a none-of-the-above option for the AI's attention. So instead of being forced to focus on some word and a really long text, it can choose to focus on this virtual sync, which helps keep it stable and focused. And this was the core of the problem. The model was essentially learning with a different brain than the one it was being tested with. The code used for training didn't support attention sinks, but the code for actually running the model did. This fundamental mismatch was the real reason the whole thing was collapsing. Now, solving this was not easy. They couldn't just go and download a patch. They had to perform some pretty complex software surgery, taking a newer version of the code, borrowing a piece from a completely different project, and then custom building the missing part themselves, that crucial piece of code that actually lets the model learn from its mistakes. So let's look at the payoff, right? To really isolate the problem, they tested it on a simple math task.
And before the fix, the model's performance, its reward, it barely improved at all over time. It was just struggling to learn even the basic stuff.
But after implementing attention sync support, just look at that. The reward shoots way up. The learning is fast, it's stable, and it converges beautifully. This was the proof. They had finally caught the real culprit behind all the training failures.
Now, with the main case solved, the team wasn't done just yet. They also had to tackle a secondary mystery, a memory bug that was just as catastrophic, a case we can call the out-of-memory heist.
See, during training, they kept hitting these crashes, and the logs revealed why. A bug was trying to allocate 180 gigabytes of memory on a GPU that only had about 140 available. I mean, it's an impossible request. No wonder it was crashing the system over and over again. They solved this memory heist with two really clever optimizations. First, they patched that mixture of experts code to stop it from inefficiently duplicating massive amounts of data. And second, they implemented a technique called sequence parallelism, which cleverly splits up these long conversations across multiple GPUs, so no single one gets overwhelmed. So, after all this, what's the big takeaway from this entire investigation? What does solving this case really mean for the rest of us? Well, the team's meticulous work resulted in 3 major engineering contributions. They restored the integrity of their training method, they custom-built that missing attention sync support, and they solved critical memory bottlenecks. And altogether, these fixes transformed GPT-OSS into a viable, powerful backbone for Agentic AI. And that really is the final verdict. This whole case shows that progress in AI isn't just about big, flashy new theories. It's often about the hard, detailed, and persistent engineering detective work that's required to make those theories actually work in the real world. And this whole case leaves us with one final provocative thought. As these AI models become almost unimaginably complex, you have to wonder, how many more of these deep, hidden bugs are just lurking beneath the surface, waiting for the next team of detectives to uncover them?